Greetings everyone, and we are from Group 3, presenting Chapter 10 Devices. And we have Garcia for the introduction.
Good day everyone, we are Group 3, dedicated to explore devices presentation. We're here to explore a journey of innovation, opportunity, and growth. Our business plan is more than just a document. It's a vision of how we plan to make a difference in the market and create value for our customers and stakeholders. So devices for input and output are essential to user interaction with computers. Not only have improvements in processing speed and storage capacity revolutionized computing during the last 50 years, but these devices' functionality and physical design have also changed dramatically. This paper looks at the change from desktop to mobile computing, its effects, and how interactions design play a key role in meeting needs of wide range of users. And now I'm going to tackle about keyboards and keypads. Text entry is one of the most common input tasks in a modern computing, and the keyboard remains the primary mode of text entry for billions of users worldwide. Despite facing criticism over the years for various reasons, the keyboard is still considered the most efficient mechanism for text entry. And the keypad? Keypads are specialized input devices that offer a range of functionalities tailored for specific tasks, enhancing user interaction with devices. This report presents notable examples of keypads, highlighting their features and intended users. Keyboard layouts. The evolution of keyboard layouts is a fascinating narrative interwoven with the history of typewriters and technological advancement. The Smithsonian Institution's National Museum of American History in Washington, D.C. features an exhibit that chronicles this development, showcasing how various designs have emerged and influenced modern typing. During the mid-19th century, numerous inventors attempted to create typewriters, experimenting with various mechanisms and key placements. By the 1870s, Christopher Latham Shaw's design gained prominence. His QWERTY layout was innovative for its time, featuring a mechanical design that minimized the likelihood of key jamming by positioning frequently used letter pairs far apart. This strategic arrangement increased finger travel distance, ultimately leading to widespread standardization. And the QWERTY. So these are the example, the key placement, and special characters. So QWERTY is the most widely used keyboard layout for typing in English and many other languages, named after the first 6 letters in the top row of the keyboard. It was designed in 19th century for typewriters. The layout was developed by Christopher Latham Schultz and aims to reduce the jamming of keys in early typewriters by placing frequently used letter combinations far apart from each other. So today, the QWERTY layout is standard on most computer keyboards, smartphones, and other devices. Lastly, this layout. Number 1, description. Arrange the letters of the English alphabet in alphabetical order. The second one, the usage. Found in some data entry terminals. The next one, advantages. Intuitive for beginners or non-typists as the layout is easy to remember. And lastly, challenges. Users with QWERTY experience may find it frustrating to switch, and studies show no significant performance advantage.
I'll be discussing accessible text entry methods for users with motor and visual impairments. We'll explore alternative input devices and innovative approaches that are helping to improve usability and efficiency for individuals facing these challenges. Typing and data entry can be difficult for people with motor and visual impairments, often leading to slow input or difficulty accessing regular keyboards. To address these challenges, various alternative methods have been developed. Today, I'll walk you through some of these innovative approaches and technologies that make text entry more accessible. People with motor impairments can still use standard keyboards, but often at a slower pace. To support them, adaptive keyboards have been created. These keyboards have lowered keys, making it easier to press the right ones. Additionally, On-screen keyboards can be controlled using alternative devices like head pointers or oversized trackballs, reducing the need for precise hand movements. Text entry speed and accuracy can be further improved by adding features like dictionary-based auto-completion and automatic error correction, which helps users input more text more efficiently. For those with visual impairments, specialized non-visual text entry methods are available. For example, Prick and Put and Braille Touch allow Braille typing on smartphones, offering one-handed or two-handed input for easier navigation. These methods are particularly effective for users who rely on touch screens and can't see the keys. By using touch-based Braille input, these technologies allow visually impaired users to communicate more effectively and independently on mobile devices. Some solutions move beyond traditional keyboards entirely. One example is Dasher, which allows users to select letters and words in a continuous 2D predictive stream. Dasher is also compatible with brain-computer interfaces, enabling individuals to input text using only their brain signals. Another example is the Orbitouch keyless keyboard. This device uses two inverted bowls that allow the users to rest their hands comfortably and make selections with minimal fingers and wrist movements, which can be especially helpful for users with conditions like carpal tunnel syndrome. Another set of text entry methods uses pointing devices like mice, touchpads, or even eye trackers, allowing users to enter text without needing a physical keyboard. Additionally, wearing devices such as wristbands or rings are being developed to support text entry on the go. Speech input has also become a popular method, particularly in mobile contexts, as it enables hands-free operation and is widely accessible across many devices. Now, we'll be looking into the design of keyboard keys and the ways in which they are defined to support usability and efficiency. From tactile feedback to specialized layouts, keyboards have evolved significantly to meet various user needs. Keyboard keys are carefully designed to enhance typing speed, accuracy, and comfort. The main goal in their design is to create a balance between usability, feedback, and efficiency. Most keys have a slightly concave shape, which allows fingers to make a sure and secure contact. The concave design improves control, preventing fingers from slipping off the keys. In addition, a matte finish on the key surfaces reduces reflective glare, making it easier to see the keys and ensuring better accuracy by preventing slips. Key design also considers the amount of force and displacement needed for a press. Most keyboards require between 40 to 125 grams of force and a travel distance of 1 to 4 millimeters. This setup enables fast typing with minimal errors while providing the right amount of tactile feedback. A slight click sound on a pressing key helps confirm the press, which is critical for touch typing. Unlike standard keyboards, membrane keyboards have a non-moving surface, so they lack the tactile feedback provided by a click. This makes them less suitable for extensive typing. However, membrane keyboards are incredibly durable, which is why they're often found in a high-use setting such as a fast food restaurants, factories, and amusement parks. To ensure accessibility, certain keys are made larger, including the spacebar, enter key, shift key, and control key. This makes them easier to access reliably during typing. Some keys like caps lock and numlock also have indicator lights or physical locking mechanism to show their status, which improves usability and reduces accidental presses. Cursor keys or arrow keys are often arranged in an inverted T layout, which allows users to place their finger in a way that minimizes hand movements. This is ideal for efficient navigation. An alternative cross arrangement can be more intuitive for beginners, and some keyboards allow the numlock to toggle the number pad into an arrow mode, further expanding navigation options. In gaming and other applications, letter keys like WASD are frequently assigned as movement controls to reduce hand movements between navigation and action keys. Another useful feature is auto-repeat, where holding a key continues to enter characters until it's released. This feature can improve typing speed and is customized to support younger, older, or motor-impaired users. Text entry methods have evolved from numeric keypads to more advanced solutions for touchscreens and small devices, meeting the needs of diverse users of mobile technology advances. As mobile devices continue to evolve in size and form, text entry methods must also adapt. With users from different backgrounds and abilities relying on mobile devices, text entry has shifted from traditional keypads to more flexible, accessible methods. In the early days of mobile phones, text entry relied on numeric keypads, which where each key represented multiple letters. This multi-tap method requires users to press a key several times to select the correct letters. Predictive text technologies like T9 and Letterwise later improved their typing efficiency, especially for longer messages by using dictionaries and probabilities to suggest words as user type. The 2007 launch of Apple iPhone marked the turning point in text entry. Touchscreens become more popular, leading to the widespread use of soft keyboards, which are visual keyboards displayed on a screen. These keyboards can dynamically adjust their layouts to fit different languages or display settings. However, soft keyboards lack the tactile feedback of physical keys, which can affect typing speed. To address challenges with touchscreen typing, gesture-based methods like Swipe and ShapeWriter allow users to trace words without lifting their finger, enhancing speed and accuracy. Additionally, the Shift technique helps combat the fat finger problem, where fingers cover the target key. Shift displaces the key being pressed, improving visibility on touchscreens and increasing typing accuracy. For those who prefer handwriting, devices now support text entry using finger or stylus-based input, though accuracy varies. Systems like Graffiti and EdgeWrite simplify character set, making them more recognizable and accessible for users with disabilities. EdgeWrite, for example, uses physical borders to help guide input, improving accuracy for users who may have difficulty with standard handwriting recognition. Text entry on smartwatches presents technique challenges due to their tiny displays. Zoom board is an innovative approach that allows users to zoom into the keyboard as they type, making it possible to accurately press even every small keys. This type of adaptation is crucial for effective text entry on compact, wearable devices. Overall, the evolution of text entry on mobile devices has focused on creating more adaptable and accessible options for diverse users. From early keypads to soft keyboards and alternative input methods, each new technique brings us closer to universal usability across all types of mobile devices. Modern touch display allows users to directly interact with content through gestures like tapping, dragging, and pinching. This direct manipulation reduces errors, speed up tracks, and improves satisfaction. Meanwhile, pointing devices are critical for tasks like computer-aided design or air traffic control, where precise selections are necessary. These devices vary based on physical attributes such as a rotational movement and positioning methods from relative to absolute mapping. The design space for pointing devices is diverse as they are created to support a wide range of tasks across various devices. This richness is designed enables flexibility and efficiency for users, whether they're interacting with a small smartphone or a large control panel. Looking ahead, we can expect even more innovations in pointing devices and touch displays, especially as the need for adaptable, accessible interfaces grows. Pointing devices are useful for 7 types of interaction tasks. First is select. Choosing from a set of items, this technique is used for traditional menu selection, tile identification of objects of interest, or marking an object in a slide deck. Second is position. Choosing a point in a 1, 2, 3, or higher dimensional space, positioning may be used to place shapes in a drawing, to place a new window, or to relocate a block of text in a figure. Third is orient. Choose a direction in 2, 3, or higher dimensional space. The direction may rotate a symbol on the screen, indicate a direct or motion, or control the operation of a device such as a robot arm. Fourth is path. Defined as a series of positioning and orientation operations, the path may be realized as a curving line in a drawing program, a character to be recognized, or the instructions for a cloyly cutting or other type of machine. Fifth is quantify. Specify a numeric value. The quantify task is usually a one-dimensional selection of integer or real values to set parameters, such as the page number in a document, the velocity of a vehicle, or the music playback volume. Sixth is gesture. Perform an action by executing a predefined motion. Examples of gestures include dwelling on an object to bring up a context menu, swiping to the left or right to turn a page forward or backward, and pinching or separating your fingers to zoom out or in. Seventh is text. Enter, move, and edit in 2D spaces. The pointing device indicates the location of an insertion, deletion, or change. More elaborate text tasks include centering, setting margins, and font sizes, highlighting boldface or underscore, and page layout. While all of these tasks can be performed using a keyboard by specifying directions that require training, in the past, the keyboard are used for all of these purposes. But now most users employ pointing devices to perform the tasks more rapidly and in fewer errors. Expert users can further improve performance by using keyboard shortcuts for tasks that are invoked frequently. Examples are Control C followed by Control V to copy and paste. Here are some of the pointing devices that we use. Another way to think about pointing devices is whether they use absolute or relative input. Touchscreens, graphic tablets, and eye trackers also use an input model where the input motor space is directly mapped to the output visual space. This is called absolute input, since 1 point is motor space corresponds to 1 point in visual space. Relative input, on the other hand, deals with transitions and rotations from a current position and includes devices such as the mouse, joystick, and trackball.
Pointing devices are essential for interacting with computers, allowing us to control the cursor and select objects on the screen. We'll explore two main categories: direct control and indirect control pointing devices. Direct control pointing devices. Direct control pointing devices allow users to interact directly with the screen. Touch screens. Advantages. Natural affordance eliminates keyboard suitable for novice users. Challenges. Imprecise pointing, early models, lack of users verification, evolution. High precision designs, left-up strategy for accurate pointing, mobile revolution. Transform tablets and phones, making direct interaction natural. Styluses. Advantages. Familiar and comfortable feel, minimize hand screen occlusion. Challenges. Need to pick up and put down potential for unintentional touches. Risk of losing styluses. Indirect control pointing devices. Indirect control devices separate the input motor space from the output display space. The mouse. The most common direct pointing device, appealing due to its cost, ability, and comfortable hand position. Advantages. Easy to press buttons, rapid movements, precise positioning with small finger movements. Challenges. Requires grabbing, consumes this space, requires separate attention for motor and display. Pick up and replace action needed for long motions. Trackball, joystick, directional point pad, pointing stick. Briefly describe each device, highlighting their advantages, disadvantages, and typical applications. Comparison of pointing device. Each pointing device has its strengths and weaknesses depending on the task and user's needs. Direct versus indirect. Early studies found that direct pointing devices were faster but less accurate. Task-specific performance. The performance of pointing devices varies depending on the specific task. Keyboard shortcuts. While cursor keys can be faster for short distance and tasks that mix typing and pointing, many users prefer the mouse due to the lack of keyboard and shortcut knowledge. Comparison of pointing devices. Challenges for users with disabilities. Joystick and trackballs are preferred due to their fixed location, small footprint, and operability with small residual movements. Vision impairments. Pointing devices are challenges for users with vision impairments. Well-designed cursor can help, but indirect control devices are not practical. Touchscreen interface can be more easily explored and memorized when speech synthesis or signification is available. Tactical graphics can be produced using their proper expansion machines and placed on top on touchscreen for use by blind users.
So the feet slow, is a predictive model on human-computer interaction and ergonomics that describe the relationship between the time it takes to move to a target and the distance and the size of the target. It was introduced by psychologist Paul Fitts in 1954 and is often used to understand and improve user interface design, particularly in terms of ease and efficiency of pointing command using a touchscreen. Voting tablet allows user to read text aloud via headphones, mark votes with checkboxes, and to communicate verbally. Blind or disabled, user can use a detachable keypad with or without voice. Since the time to start and stop moving is constant, an effective equation for the movement time, or MT, for a given device such a mouse turns out to be MT equals A plus B log 2 DW plus 1, where approximates the start-stop time in seconds for a given device, and B measures the inherent speed of the device. Both A and B need to be determined experimentally for each devices. For example, if you were 300 milliseconds and were a blind student uses touch graphics tactile map mounted on a touchscreen on the right, a different obese overlay is used to learn the location of states and capitals with a pen providing audio description. This long mathematical equation provides accurate prediction for movement time in a various situations, including device weight, target shape, and arm position. It has been applied to a high-precision touchscreen where studies show fine-tuning finger motion on small targets, leading to a three-component equation for precision pointing movement time, where PPMT equals A plus B log 2 DW plus 1 plus C log DW. Variation in the law are due to factors like direction of motion, device weight, and target shape. Fitts' law, a precision pointing movement model, may require refinements for specific populations such as young children or older adults as age significantly influence precision. So, novel pointing. Novel pointing devices are alternative point tools that differ from traditional pointing devices like the mouse, keyboard, or trackpad. These devices offer new ways of interacting with computers or digital systems, often designed to improve precision, efficiency, or accessibility in specific contexts. So here's are the example of novel pointing devices. First, stylus and graphic tablets, a pen-like device used in a surface to directly control the pointer. It is commonly used in design, art, and handwriting application. Second, eye tracking system. This device allows users to control the cursor by tracking the movement of their eyes, commonly used in assistive technologies for individuals with mobility impairments. Gestures. Third, gestures-based devices. Devices like the leap motion sensor that detect hand gestures in the air to move or control on-screen elements. Here are the purpose of novel pointing devices. Enhanced precision. Many novel devices are designed to give users more control or precision, especially in specialized fields like graphic design or 3D modeling. Accessibility. Some devices are created to help users with a disability interact with computers more effectively. And the last one, new interaction methods. Devices like touchscreen and gesture-based controls offer more intuitive or natural ways of interacting with technology. Overall, novel pointing devices aim to improve user experience by offering new ways to control and interact with digital environments beyond the standard mouse and keyboard. Thank you.
Displays. The display is the primary source of visual feedback to users from the computer. It has many important characteristics such as physical dimension, where it is diagonals in size and depth, resolution, number of pixels, number of available colors and color correctness, luminance, contrast, and glare, which is the brightness and visibility. Next is power consumption, where it is about energy usage. Refresh rates. It is suitable for animations and videos. Cost and reliability. The affordability and durability. Next is the usage characteristics of a display, or portability, the ease of transport. Privacy, personal versus public use. Ubiquity, the availability and accessibility. And simultaneity, the number of simultaneous users. Examples of displays. First is mobile phones. These are portable and private. Next is large displays. Social interactions such as video games. Salient displays. These are information in public spaces, for examples in mall and museums. Next is whiteboards. It is for collaboration and brainstorming. Next is immersive displays. It is the virtual experience for learning or recreation. Display technology. Evolution and types of display technologies. First is we have the modern display technologies, which are the LCDs or liquid crystal displays. They are thin, lightweight, and has low power consumption. Next is plasma displays. They have flat profile, high brightness, readable from the side, and higher power consumption. Next are LEDs or light emitting diodes. So they are available in many colors. They are also used in large public displays and head-mounted displays. OLEDs. Next is OLEDs or organic LEDs. They are energy efficient, durable, flexible, and used in wearable and rollable displays. Next is electronic ink. They are paper-like resolutions, extend battery life, which are used in e-readers, for example, Kindle or Nook. Next are the innovative display solutions. So first are Pico projectors. They are tiny projectors for mobile devices, enhancing collaboration. Next is Braille display. They are for blind users, providing tactile feedback with up to 80 cells. Next is refreshable graphic displays. They are prototypes with thousands of pins for detailed graphics. Next is we have health and environmental considerations. First is visual fatigue and stress, mostly due to overall work environments rather than the displays themselves. Next is radiation exposure. They are addressed by manufacturers and government agencies. Next in displays are large wall displays. So here are the integration and types of large displays. So type of large wall displays. First is there are informational wall displays. They are shared views for users at a distance. They are effective in control rooms for system overviews. Next is we have interactive wall displays, where it allows close interaction and discussion. It is suitable for collaborative environments. Next is multiple desktop display. They connect multiple screens for more visible windows and documents, enhancing productivity. Next are the applications and benefits. So in control rooms, they are used in military, utility management, and emergency response for situational awareness and coordination. Next is for collaboration. Teams can view applications running on different computers on a single display. Next are the technologies and solutions. So first we have rear projection and tiled LCD displays. Rear projection offers seamless displays but requires space. Tiled LCDs are cost-effective with visible seams. Next is extreme scale displays. For example, in Stony Brook University Reality Deck with over 400 high-resolution screens. Next is specialized software. Frameworks like Polychrome distribute rendering and merge input across multiple computers. Next is we have interactive techniques. First is new interaction methods, freehand sketching and novel menu techniques for fluid interaction on large displays. Next is digital whiteboards. Touch-sensitive screens, for example, smartboard, simulate traditional whiteboard with added digital functionalities. So here are benefits and challenges of multiple desktop displays. The advantages. First is we have enhanced productivity. It is useful for creative tasks requiring multiple tools, for example, web development with various editors and preview windows. Next is side-by-side comparisons. Facilitates documents comparison, software debugging, and reasoning with multiple information sources. Next is user appreciation. Empirical evidence supports their benefits for users. And here are some challenges. First is we have clutter. Risk of clutter displays as physical size increases. Next is direct manipulation, difficulty in managing objects due to distance on large displays. We also have innovation and solutions. First is cursor tracking, improvements needed for easy cursor tracking across displays. Next is focus switching, rapid switching between windows via strategic overviews. Next is we have automatic layout, strategies for automatic window layout and coordination. Future trends, prevalence. As display costs drop, multiple desktop and larger single displays will become more common. Next is we have tabletop horizontal. So tabletop displays for collaboration. Horizontal surfaces. It encourages collaboration and discussion. Application. Ideal for creative design, problem solving, and real-time resource management. It also has multi-touch technology, which supports multiple users and interactions simultaneously. For example, we have Microsoft Surface, Surface 2, Perceptive Pixel, Surface Hub, and Circle 12's Diamond Touch. User identification. Diamond Touch can distinguish between different users. Flexible orientation, usable for any position around the table. Physical object, can be used to mark positions and aid design sessions. Advanced displays, potential for 3D interactions using stereoscopic, volumetric, or head-mounted displays. And lastly, we have integration with mobile devices. It enhances collaborative capabilities.
Heads-up and head-mounted displays. So heads-up displays, which are also the abbreviations of HUDs, project information onto a partially transparent surface like a car windshield, allowing users to see information without looking away from their surroundings. So head-mounted displays, HMDS, which are the abbreviations for this, are worn on the head and then provide a similar function. So they can adjust the information shown based on the user's head movement, creating a more immersive experience. And then the examples of HUDs and HMDs include airplane cockpits, virtual reality devices, and smartwatches. So the key considerations for designing HUDs and HMDs includes the visibility, ensuring clear information in various lighting conditions, task optimization, designing for specific tasks and minimizing distractions, user experience, considering factors like comfort, field of view, and audio quality. So we moved up to the mobile device displays. So mobile devices are becoming increasingly popular and have the potential to improve various aspects of life, such as healthcare, education, and travel. So the key applications include key medical monitoring. Devices can alert doctors to changes in patients' vital signs. Next is educational tools. Students can use mobile devices to gather data, collaborate on projects, and solve problems. Emergency response. So first responders can use mobile devices to assess dangerous situations and coordinate of efforts. Personal devices, smartwatches, and other wearable technology offers offers features like fitness tracking, communication, and entertainment. And then the design considerations for mobile devices include optimizing for repetitive tasks, minimizing data entry, offloading complex tasks to desktop computers, considering a wide range of actions like monitoring information, gathering data, and collaborating, and then ensuring readability in various lighting conditions and for users with poor eyesight.
Overall, mobile devices offer a versatile platform for personal and professional use with the potential to enhance our daily lives. And we have upcoming next is the mobile device interaction design. So, responsive web design is crucial for creating websites that look good in all devices, from smartphones to tablets to computers. And it involves designing for mobile devices first and using techniques like unobtrusive, unobtrusive dynamic behavior and progressive enhancement to ensure compatibility with different browsers and devices. So the key considerations for this mobile device interaction design. So on one-handed interaction, it's designed for users who may have only one hand available. Multiple devices, it considers different screen sizes and input methods for customers and for users. Accessibility, they ensure that mobile devices can be used by people with disabilities. And the next is remote services provide options like text to speech, sign language, language translation for users who may need them, and to access communication.